Hello everyone and welcome to 9.1 Continued. We're going to begin today with example 4. It says find the standard form of the equation of a parabola with vertex at 0, 0 and a focus at 0, -2. So what I'd like to do on this particular problem, and really several of these questions where all you're given are maybe a couple of pieces of information, in this case the vertex and a focus, is I like to graph a rough sketch. So let's draw a quick little XY axis. Okay, and our vertex here of 0, 0, and our focus 0, -2. So just based on that information alone, we can assess that this particular parabola is going to open down. Let's just draw a quick sketch. It doesn't have to be really that precise. Just draw your picture to get the basics down. And what we can assess from here pretty nicely is that the distance between the vertex and the focus, we know pretty nicely here, just 2 units. That's actually our p-value. Okay, and because it opens down, we're actually going to write down p equals -2. In the context of the equation now, which again, if we reflect back on the notes from a couple days ago, we can see here again that we've got x minus h quantity squared equals 4p times y minus k. That's a up or down opening parabola. Or y minus k quantity squared equals 4p times x minus h. That's a right or left opening parabola. So we already know it opens down, therefore it has to be x minus h quantity squared equals 4p times y minus k in parentheses. We also know though as well, because it opens down, p happens to be negative. So we're going to use that equation in the appropriate context here and write it down accordingly. So x minus, and I'm going to write 0 because I do know that h and k are both 0, and we can say therefore x minus h, in this case 0 squared, equals 4 times our -2 value, our p value we can substitute in there, and then times the quantity y minus k, which we know is 0. So that's pretty simple. We now have x squared, and that equals -8, and that then leads to, of course, well, times y. Y minus 0 is just y. So the equation of this parabola is x squared equals -8y. Now, in the traditional sense of graphing a quadratic equation, we'd want y to be isolated, and we could still do that. Y equals -1/8 x squared if we wanted to look at it from that perspective. But from this kind of new standard form perspective, we'll leave it as is as our final answer. All right, next, example 5. So example 5 says find the vertex, focus, and directrix of the parabola given by x squared minus 2x minus 16x, or 16y, pardon, minus 31 equals 0. Okay, so we'll go ahead and start the process of completing the square. Anytime you have an equation of a conic section that doesn't traditionally look like a typical parabola or circle or later ellipse or hyperbola, we're going to probably have to complete the square. So we'll go ahead and do that. First, by kind of differentiating between the x squared -2x, but also the other two terms in this case, the -16y, which I'm going to add to the other side, and it becomes positive 16y. And the -31 added to the other side, becoming positive 31. So from here, if it isn't already obvious, completing the square is necessary. In the final assessment of things, it will look like the standard form we're typically used to seeing. So we have this. Go ahead and note that plus something on the left, but also plus something on the right, which really just speaks to you completing the square, particularly on the left side, noting that b is equal to -2. b over 2 is equal to -1. Therefore, when you square that, b over 2 squared is just 1. So that's the number we write here, as well as there on the right side. This is now a perfect square trinomial, not surprisingly, and we can write it as a binomial squared, x minus 1 that is, if you recall. X minus 1 comes from the b over 2 quantity that we got. And then that equals what? 16y plus 32. Now this is really not a traditional looking standard form of a parabola yet, until we just do one more thing, and that's factor out, in this case, 16 to leave us with this. Y plus 2 the quantity. We're still not done. But we can assess from here really nicely actually is that our p-value, thanks to this, notably 16 equals 4p, leads to, if you divide by 4, p equal to 4. And because p is equal to 4, that being a positive number, we know that it opens up as opposed to down. Certainly it's not a right or left opening parabola because x and now y is squared. So we know it opens up, and we can graph this. I think graphing is really a smart thing to do from here. Again, I'm not going to be particularly precise necessarily. I don't have to be in order to decipher my vertex, focus, and directrix. My plotting of points will be precise, but from there really the parabola doesn't have to be perfect. So 1 comma negative 2. If you're wondering where I got that, well, here's your h and here's your k. So 1 comma negative 2, we'll go ahead and highlight as such. We know it opens up, so I'll kind of write down here 1 comma negative 2. And then my focus, thanks to the fact that p is equal to 4, will be 1, 2, 3, 4 units above the vertex. And if you simply just count, you can see here that we are at 1 comma 2. 1 comma 2 being your focus. And again, that was 1, 2, 3, 4 units above the vertex. That then speaks to, well, if you want to just do a quick sketch, doesn't have to be perfect. A parabola, of course, opening up as such. The directrix, if you recall from the beginning of the notes, will be p units below. So 1, 2, 3, and 4 down from the vertex. And that directrix equation is y equals, and again I went 4 down from already negative 2, so that should be y equals negative 6. So those are all the pieces to what I need to find in this particular case. Again, I had to complete the square to get that standard form and then make our assessments from there. The picture really does help, so please try to stay in line with doing that on most of these questions. Example 6. Write the standard form of the equation, or standard form equation, of the parabola with focus at 1, 2, and directrix at x equals 3. So we're going to draw a picture again. So our picture, again, speaks to, well, here 1 comma 2 as our focus. And I'll go ahead and label that. So our focus is, again, 1, 2. And again, our vertex, well, we don't know that, but our directrix will help us with that. Our directrix is here. It's the vertical line x equals 3. So if you recall, the vertex, well, happens to be the midpoint between the focus and the directrix, so there's really only one place for it. The vertex has to be here. Okay, and I'll label that. That vertex is, well, just count, 2 comma 2. All right, so 2 comma 2 is the vertex. We know the parabola opens left. It must, based on where the focus is and, of course, the directrix is. And therefore, my equation looks like this. So we'll go ahead and highlight y minus k, quantity squared, equals 4p times x minus h. Now when writing your standard form of the parabola, notice again, well, y is squared here as opposed to x. But y and k are always paired together, as are x and h. So this equation is perfect. All we need to do is plug in what we know. Now as far as p goes, I will squeeze that in here. The distance between the focus and the vertex being always the p-value. In this case, though, because it's opening left, p is negative 1. So when we plug things in, we'll say y minus k. In this case, k is 2, as is h. So hk is 2, 2. So y minus 2, quantity squared, and that equals 4 times negative 1 times x minus 2. We'll finish up so that our math yields the following. Y minus 2 quantity squared equals negative 4 times the quantity x minus 2. There is your standard form of your parabola that opens left. Notice the sign in front here, that's a negative, which is important, right? Not only because, of course, well, y is squared, that opens either right or left, but because it's negative, certainly it opens left. Next page, please. So on this next page, we're going to be taking a look at reflective properties of parabolas, the reflective property of parabolas. And as a note, we have this indicator here where d sub 1 equals p minus b. I'm going to add to that another little kind of version of this where p is equal to the absolute value of b. P plus, excuse me. the absolute value of b. If you're wondering where d sub 1 came from, let's reflect a little bit. Back at the beginning of the notes, d sub 1 is actually the distance between the focus and any arbitrary point on the parabola. It's also the same distance from that point perpendicular to the directrix. So that particular d sub 1 value, we're going to go ahead and calculate. Whether we know p, b, or really any one of the two of the three things here, you could say, in this equation, you'll be able to find the third. So the reflective properties of a parabola can be found in a television satellite dish. For example, any satellite signal that comes to the parabola parallel to its axis is reflected to the receiver, which is at the focus. It has to be. Otherwise, you don't get a signal. A line segment with endpoints on a parabola and containing the focus of the parabola is called a focal chord. And lastly, the focal chord perpendicular to the axis of a parabola is called the latus rectum. A line is tangent to a parabola if it intersects the parabola but does not cross it. As an example, we're going to go ahead and draw a parabolic reflector. Okay, so this parabolic reflector, and in particular I'll draw a cross-section of a headlight on a car, let's say. So let's say you had a headlight cross-section that looks something like this, very much obviously the shape of a parabola. What we'll see here is that the light source will be centralized at the focus, typically. And what happens is when the light is turned on, you'll have light rays kind of bouncing off, coming from the light source, of course, but bouncing off the reflective surface of the parabola. And then what happens is the light rays actually then bounce off and shoot parallel to the axis. So what I'll draw is just maybe a couple of light rays shooting off and bouncing off in a parallel manner as such. Okay, just to give you guys some perspective visually. Okay, and of course even the light shines like this. A couple things to highlight, as again we should note that this is your light source. And then, well, all of those rays, of course, hit and then bounce off. This light source, I should note, is centralized at the focus. Let's highlight that. But then you have some other characteristics that we need to highlight, particularly the axis, because there is another ray that is perpendicular to the axis of symmetry. It's actually the axis that we refer to as the latus rectum, or just segment, really, perpendicular. That latus rectum is another aspect of really all of these rays and segments that are observable in this particular example. And the last little part that I'll note here, we call the chord actually that runs through the focus, the focal chord. One of these focal chords I'll highlight. Just another aspect to note. Moving on now to the reflective property of a parabola. The tangent line to a parabola at a point P makes equal angles with the following two lines. One, the line passing through point P, and the focus, which the line containing the focal chord at P will be highlighted. The axis of the parabola as well is the second of two lines that we're going to identify with. I'm going to draw a quick sketch, and on our sketch we'll have a vertex of 0, 0, a focus somewhere above the vertex. The parabola will open up as such. The point P that we'll refer to, which is tangent, go ahead and highlight as such, and then the tangent line to the parabola will look something like this at point P. So this is your tangent line. And then we have other aspects to highlight. Particularly, we have some segments from focus to point P and from focus to the y-intercept, which we'll identify with in our next video and continue from there.